Hello, and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. And welcome to today's show. We've got a fantastic episode lined up again. So today we have a real expert in electrical machine design and development, Dr. Antti Lehikoinen from Smeklab. He's the founder and CEO of that business. He's someone who caught my attention a few years ago because he was doing some really interesting work in a field that was parallel to one I was working in. I've been following him since, and really, really pleased that he's agreed to record an episode today talking about his experience in motor development and motor technology and what's happening. So, Antti, welcome to the show.
Thank you.
So, if we could kick off in the traditional way, and if you could tell us a bit about your background and where you're from and how you came to be doing what you're doing now.
Okay, sure. So what I'm doing now, very briefly, like mentioned, I'm the founder, CEO, and so far the only employee of Smeklab Limited, which is a Finnish company doing consultancy on electric motor design. And how I ended up doing this, well, it was partially by accident or by chance. I was studying at Aalto University, Finland, about 10 years ago, well, closer to 15 now, trying to pick my major out of very many, very interesting options. And I ended up picking motors somehow. I'm not really sure why, but I think that is quite a typical story on people, how they actually end up doing what they do. Anyways, I did pick up motors. I liked it. I stayed on the field, got my PhD, started my consultancy roughly about the same time as the EV business started really kicking off.
And this interesting thing with people who do this today, so like you, like me, when we were sort of picking our choices for studying back, obviously not that long ago, because
not that long,
but probably a little bit longer than we'd like to remember or admit. It doesn't feel like long ago anyway. But back then, it was way before electric vehicle things, were really being talked about. Motor technology, sort of very much industrial machines. It wasn't the topic that it is today. So quite a bit of good fortune there in terms of picking that. Were you aware, do you think, at the time of how important electric machine design would become? Was that sort of was something that was talked about back then, or was it just pure sort of interest and a bit of chance?
No, I can't really say I had any idea. Well, we had EVs, of course, even back then, but they were more like a curiosity.
Yeah,
I would say.
Yeah, we had. Well, in the early days of my previous business, we had a lot of jokes in the UK about what were called milk floats. So the best known electric vehicles were for delivering milk, and they were very slow and ugly. And this was the sort of typical reference point for most people. A very, very long way from a Tesla or a Porsche Taycan. Did Finland also have milk floats, or was it some other kind of electric curiosity?
No, we didn't have such, but I think the Finnish Postal Service has been using electric vans for quite a long time now.
Right.
They are quite decent, not awfully slow or not obviously bad like that, but still.
Yeah, okay. I mean, in Finland, generally, there's some, connection to where I'm based in the north of England, where there's a sort of historic legacy of electrical machine design. But Finland, for a relatively small country, is absolutely up there in terms of electric machine design, the academic work, but also the industrial activity. A number of notable companies based in Finland, ABB, the marine business, Azipod, you've got the Danfoss business now, which was Visedo, et cetera, plus some really fantastic academic work going on. Why do you think that is? Why is Finland so strong in this area?
Okay, now I'm actually a bit embarrassed because I don't know how to answer that. I think it is indeed related to ABB, because as you may know, ABB emerged as a merger of 3 companies. There was this Axial, which was maybe Swedish, I think, and then Ryan Maughan from Switzerland. And one of them had earlier merged with Strömberg, which was a Finnish company. And that had a long history. It started in the late 19th century, I think, as a workshop kind of thing, and then started delivering motors to basically any application outside Finland.
It's great. And I guess that sort of technology-based, engineering-based, because, obviously it goes beyond just machines, but really strong country generally for technology and engineering. So brilliant. So what was your particular focus area for your PhD?
For my PhD, I studied AC losses in random wound high-speed machines.
Okay.
So winding losses, basically.
Which is an incredibly topical subject now.
Yes.
So you then went and decided to set up in consulting. What was the motivation behind that?
Well, the motivation, how to put it, I had some interest in setting up a business for quite a long time before I started blogging on machines and motors and finite element analysis maybe 1 or 2 years ago before I set up my business. Then I got a sort of a lucky break. I had a prospective client contact me to get some work done, and for that I needed a business. And I decided that, okay, the money is good enough to at least cover the expense of setting up said business. So I went ahead with it, started getting more business quite soon, and basically stayed on it. In the beginning, it was strictly part-time because I started in summer 2017, I think, while I was still finishing my thesis. After that, I continued as a postdoc in Aalto University for about 18 months more and ran my business part-time on the side. And after that, well, my contract as a postdoc ended, so I basically jumped full-time into this consulting and motor design thing.
Okay, brilliant. And so give us an example of a sort of typical job that you would find yourself doing now. Where do what are people calling you in to solve?
Well, obviously I help businesses with motor design, and more specifically they are usually such businesses that either need or use custom motors but don't really have that kind of expertise in-house. So companies who are closely dealing with motors but are not making them themselves. And what kind of projects I'm working on? Well, I seem to have like 3 semi-spontaneous focus areas.
Okay.
The first one is EV or traction motors in general, quite obviously.
Yeah, a lot of activity in that space at the moment.
Yes. The second one is high-speed machines like compressors or flywheels, probably because we have quite a strong industrial experience here related to them.
So, and when you say, because obviously high speed in EV traction is a thing, but I think the high speed you're talking about there on industrial is maybe another, how high is high?
Okay, yeah, that's actually one of the things that is not clearly defined.
Okay.
different authors may mean different things by high speed. They can be speaking about RPM or the frequency or the surface speed of the rotor. But in the industrial scope, I would say it begins at 30,000 RPM and goes up from there.
Okay. Yeah. Okay. Great. So, because a high-speed traction motor might be 18,000 RPM, but that's low speed in comparison. So 30,000. So kind of direct drive for turbo machinery, that kind of application.
Exactly.
Right. Okay. All right, and that's two. Where's the third?
Yeah, and then the third area is aviation motors. So for electric aircraft, air taxis, stuff like that.
And that's we see a lot of, well, I would say we see a lot in the press. I think I have quite a big echo chamber in terms of looking at electrification stuff all the time. There's quite a bit of activity around electrification in aircraft at the moment. Do you see that as a growing area or a different different?
Yeah, I think it definitely is coming. I mean, electrification of aviation, maybe not as soon as you might expect based on the media publicity that is being pushed around at the moment, but it will be coming. I'm quite certain of it.
And there's I think sometimes people don't realize there's kind of two, well, there's more than one kind, but the you've got the really far out kind of eVTOL electric sort of air taxi type concepts, but then in more conventional fixed wing aircraft, you've got electric propulsion systems, but then also there's quite a bit of activity around electrification of sort of accessory systems and somewhat hybridization in conventional fixed wing aircraft, and actually in rotary aircraft, so hybrid kind of drives for helicopters and things like that, kind of people kicking around. So there's sort of at varying degrees of very extreme, completely different airframe concepts, multi-rotor, like big drone type stuff, right up to it's probably going to look exactly the same as a conventional aircraft, but it's got a few more electrical devices and systems on. Is there a particular type that you are more seeing more activity around? Is it more on the sort of conventional fixed wing, auxiliary drives and actuators stuff, or is it the more sort of extreme multi-rotor eVTOL area?
Okay, that's actually a very good question. I'm definitely not an expert on this topic, but I think the electrification of the auxiliary systems, it has been going on for about, 40, 50 years now. Because in the early days, it used to be like hydraulics or pneumatics only, or even wires and cables.
Yeah.
And slowly they have been replaced by motors more and more. And well, yes, I expect that trend to continue.
Yeah.
And on that note, there have been plans for about how to put it, partially electric propulsion, either by having like a starter generator inside a conventional jet engine or the so-called boundary layer ingestion or injection, what is it, which is basically works by adding small motors and fans somewhere near the body of the machine to basically decrease the aerodynamic resistance or stuff like that. And then you, of course, have those actual electric propulsion. And based on feasibility, I would maybe divide it into 3 categories. The furthest away are full-on electric jet aircraft, the kind that takes hundreds of passengers over the Atlantic. And at the moment, there's no way, at least batteries are going to manage that.
Yeah.
And in between, you have maybe the eVTOLs, so electric air taxis in practice that are actually flying at the moment, some prototypes at least. But they have been gaining quite a lot of criticism recently as well, because, well, various reasons the certification process might be difficult. I hear, again, definitely not an expert on this at all. And also the business or the market might simply not be there.
Yeah, they're very different aircraft to certify compared to, conventional aircraft. And there's a sort of tipping point. I mean, I don't fly a helicopter really for two reasons. One, I have no skill to fly one, and two, I don't have the money to be able to buy or operate one. So, even if I did have the money, I don't have the skill. So the kind of potential to open up that sort of aircraft with more autonomous systems, either fully autonomous or something that's basically as easy to fly as it is to drive a car, is quite interesting to be able to get in and kind of go. But it's a long way off because the whole system isn't really set up to deal with that kind of aircraft. So in your line of work, is it are you more sort of seeing inquiries for yourself on the conventional aircraft systems then, or is it the eVTOL area where you're being asked to look at drives?
Well, how to say it? I haven't got that many queries at all, but at the moment it's something like a 40-60 split between eVTOLs and conventional aviation, with conventional being in the small majority.
That's interesting. And it must be then, well, this could be the wrong assumption, but presumably you're working with companies outside of Finland. There's you must be sort of dealing relatively globally with people.
Yeah, very much so. I have a few clients in Finland, but all the others are basically from Western Europe and then the Americas.
Yeah. So based on that work, you got the three areas: the high-speed machines, the traction machines, and the aviation. Do you see any kind of common trends or issues across those sorts of machines? What do you see in the market?
Well, how to say it? Well, this is not a trend per se, but it's more like an observation. I think the motors field is developing quite fast at the moment. And why it's doing that is very interesting, because I think the building blocks, they have existed for about, 20, 30 years now. But earlier, there hasn't been demand for, let's say, any kind of, well, some kind of, but not the kind of specialized high-performance machines that we are seeing now. Because earlier, back in the day, what motors did, well, they would be driving all kinds of machinery, from kitchen appliances into huge pumps used in mines and so on. Or they might be pulling a train or propelling an icebreaker maybe somewhere. But that was about it. So nobody was really caring that much about the performance of the machines. And by performance here, I mean like a combination of efficiency and power density. But now with the booming popularity of EVs has basically kicked that demand into high gear.
Yeah. And is it, do you think a thing, so I was wondering about this just yesterday with someone, that effectively an awful lot of how a motor is designed today, like we don't necessarily even realize it because it's buried in the modeling tools and simulation tools, but there are kind of old design principles and empirical relationships and data that kind of sit behind how we do a machine design, which haven't necessarily had to be challenged or needed to be challenged. Do you think that we're starting to see a lot of sort of fundamental rethinking around some of those rules in terms of how we would design a machine, or these sort of empirical relationships that we've relied on for a long time?
Well, I would say both, and basically the kind of, okay, let's put it that way. If you open a book on motor design. Most likely it's quite old, a couple of decades at least from the first print.
Yeah.
So it has been written with the kind of industrial machines in mind. So the rule of thumbs written there for sizing the machine, like what kind of anything you can have. They can be a bit out of date if you consider like more demanding applications.
Yeah.
So in that sense, we are indeed moving beyond the old principles. But on the other hand, most of the machines today, even today, they are still based on the same machine topologies. So the kind of machines that have existed for quite a long time in one form or another.
Yeah. And so some of those things might be, like, for instance, when you look at the design rules around insulation systems, I think the insulation classes, the historical ones, stop at about 180 degrees. But we now have, in particularly high performing machines, regularly going up to sort of 200 plus 220. So we're into kind of uncharted, well out of those sort of standard design rule territory on something as fundamental as insulation resistance.
Yeah, you are right. So basically, you can apply and you have to apply the traditional design approach or the principles, let's say, but you can't apply it exactly as it's been written because, like mentioned, we are moving beyond it all the time.
Yeah. And do you think part of what is driving that? So in the past, the machines were developed. You sort of you plotted the required life cycle for the machine, which for an industrial machine was long, 50,000 hours or something, or maybe even more. Design life, and you sort of have these lookup tables where you kind of went, well, that's my design life, and that's then these are all the maximum permissible properties across here. But is it, do you think, just a function of those design lives? Because of consumer goods and vehicles and stuff, the design life is shorter than it might be for an industrial motor, or do you think there's genuinely sort of improvements been made in fundamental material technology and things like that?
Yes, of course there are several of them, at least. Maybe the key one of the key ones at least, was the invention of rare earth magnets, like the neodymium magnets I think it was in 80s.
Yeah.
Because those basically presented a stepwise improvement against what they had back then. Because earlier you had ferrite magnets and similar, which could support flux densities up to 0.4 Teslas or something. And then came the neodymium versions, which even the very early iterations could go up to 1 Tesla or something like that. Yeah. And now we are, of course, pushing the 1.4, 1.5 limit. Yeah, the second enabling factor was the introduction of power electronics, obviously.
Yeah.
Like IGBTs. Well, they had some things earlier, like thyristors and stuff like that, but they were mostly restricted to like high-end demanding applications, like icebreakers, trains, stuff like that, I think.
Yeah, and power electronics are now developing really rapidly, very high efficiency, high frequency switching devices. So there's the potential for more and more development on that side to have either simply higher RPM machines or do really interesting things with the switching and control. So things like switch reluctance machines or interior permanent magnet where you've got partial reluctance effects and stuff like that. Do you think, again, something I was talking about recently was the advent of better simulation capabilities? I mean, at the moment, we're actually just sort of moving into 3D simulation being widely available for electromagnetic systems. and obviously much higher power capability, meshing for thermal and fluidic, is the sort of improvements in simulation techniques and tools and speeds. Is that a contributing factor as well, do you think?
Yes, of course they are useful, especially for pushing the envelope or getting a highly optimized machine. Because when you are aiming for something that is highly optimized, then of course you need high fidelity simulations to predict the performance of the machine and to be able to actually optimize it.
Yeah.
If you don't have that capability, you are basically reduced to prototyping a lot, which again then takes a lot of time.
Yeah, rig time. But we all like a bit of rig time.
yeah, it's good.
So then, so you mentioned about different machine topologies earlier. Can we expand on that a bit? What do you think the kind of main topologies are that we're seeing at the moment?
Well, depends on the application. That's the boring answer.
Yeah.
In the industrial scope, they are mostly induction machines because they are, well, cheap, reliable, they work, they start directly on a line, stuff like that.
Yeah.
If we move into traction applications, they are almost all of them are permanent magnet machines with the kind of V-shape interior permanent magnet rotor that I think almost anybody has seen in some picture or video at some point in their life.
Yeah.
So those are the main workhorses at the moment.
Yeah, there's some interesting. I mean, on traction motors, we've got some people making noises again around wound rotor machines. So BMW talking about that. Obviously, Renault been doing that kind of machine for a while. Do you think there's real potential for wound rotors to come back? I mean, it seems a bit counterintuitive actually, because they're typically low rotor magnetic field potential of that sort of machine. So why do you think people are looking at that kind of thing again?
Well, there can be several things going on. One is that, well, they don't obviously have rare earth permanent magnets.
Yeah.
Which is in a way a good thing.
Yeah.
Okay, maybe I will have to stress that the rare earth materials, they are not rare in the actual sense of the word, but they still do present some sort of a supply chain issue.
Yeah.
Because at least as I understand is that most of the commercially viable deposits of rare earth materials are in China at the moment. So there's like a geopolitical uncertainty element going on.
Yeah.
And if you could get rid of that, that would of course help some people sleep better at least.
Yeah. Why do you think though? So I mean, it surprised me to see those machines sort of making a resurgence, because the go-to for me in that instance would be an induction machine rather than a wound rotor. So why do you think people would choose a wound rotor over an induction machine?
Okay, that's a very good question. Actually, I don't really have an answer to that, because they are indeed very similar in terms of the challenges they face. The main one being that you have very high losses in the rotor if you compare to a permanent magnet machine, of course, and you will have to cool those losses somehow.
Yeah.
Take the heat away, so you will have to design a cooling system for that. One thing might be, I'm not fully certain about this, I haven't gone through the math myself, but I think you might be able to get a bit more torque or power action machine for the same rotor losses, which are the difficult one to cool.
Yeah.
But again, I won't fully get behind that claim because, like I mentioned, I haven't worked it through myself yet.
Yeah.
I should probably have to do it at some point when I have the time, which is never usually.
Yeah. It's because I mean, Tesla have quite successfully used induction machines, and sometimes combined with IPM in the driveline. but then these wound rotors sort of introduced some other challenges with wear and tear on brushes and things like that. And there was a sort of argument saying it was potentially lower cost, but I think if you look at the cost build up on a wound rotor machine versus an induction, I don't imagine it's all that different. And in some ways, actually, probably could make an induction machine cheaper than a wound rotor, I would think. So had me scratching my head a little bit. I was wondering if it was to do with zero speed torque, or the other interesting one with vehicles is we're all basically all guilty of ridiculously over specifying the motors. So the target everyone is aiming for is a really good drive cycle efficiency, which is partially loaded, light loaded conditions. But then the sort of peak power of the machine needs to be, much higher than what it's actually ever going to do for most of its life and the key driving cycle. So that perhaps that trade off in partial load versus the sort of delta between continuous operating and peak. Maybe you can stretch that the relationship between continuous and peak further in a wound rotor machine.
Yes, at least the one thing that they do have going on for them is that you can easily control the field or the flux density that the machine is operating at. Because in a permanent magnet machine, the permanent magnets are producing the flux, and they are doing it all the time, no matter what you do.
Yeah. So
in the extreme case, let's say you are idling the machine at high speed. You basically are driving on a highway and decide to slow down very slowly, so you simply cut all the power to the machine. In a permanent magnet machine, you will still have relatively high losses, no load losses, because of the permanent magnet flux causing losses in the iron. Yeah. In a wound field machine, you can, of course, cut the excitation altogether.
Yeah.
And you only have to do with the mechanical losses in the bearing and friction with air, stuff like that.
Yeah.
So indeed, in the low load, high speed operating ranges, I think a wound rotor machine can be much more efficient, or at least, let's say, significantly more efficient than a permanent magnet machine.
And what about if you compared in that same situation the wound rotor to the induction machine? How do you think that would? Because it's quite similar in terms of you can control the induced fields in the rotor quite well in that situation as well, or not? Probably actually not as much as you could with a wound rotor.
Yeah, that's a tough question. They are very similar, at least.
Yeah,
that's certain.
Okay. So, and one other type of machine that fascinates me in radial flux. So we're talking about interior permanent magnet, which is, as you said, very, very common for traction motors, induction machines, which don't have permanent magnets in the rotor, and you induce the rotor magnetic field. Wound rotor machines, which also don't have permanent magnets in the rotor, but it's effectively an electromagnet that you control. And there's a third type, which is a switch reluctance machine, and they've kind of been on and off for some time. And people kind of coming into the market now with switch reluctance machines for propulsion or traction purposes. And the advantage being you don't have rare earth magnets in the motor again, and you can control that rotor magnetic field. And perhaps the advances in power electronics we were talking about earlier partially responsible for now these machines being more viable. But what are your thoughts on switch reluctance motors? Do you see them having a significant place?
Well, let's just say I'm not convinced yet.
Okay.
Again, I haven't gone through the mathematics or design process myself, so I don't have that great of an idea about what they are capable of.
Yeah.
But it's quite easy to see that they are not being used in any major applications right now.
Yeah.
At least not as far as I'm aware of.
Yeah. Why do you think that would be? What's the sort of limiting characteristic of that sort of machine?
Well, there are several they are traditionally at least thought to be noisy and vibrate a lot easily. Maybe it's possible to design around that nowadays, but it's still difficult. It's something that you will have to work on.
Yeah.
Then what they can and can't do, I'm not sure there is anything they can do that some other topology can't do pretty much just as well in a more easy to design way.
Yeah. Yeah. So just sort of perhaps that they're interesting, but don't tip the balance in any particular way enough to make it worth commercializing, plus the problems to do with noise and things. And you always end up with this, you've got rotor cooling problems potentially with switch reluctance machines, and also relatively low power density, because you can't really get very high rotor magnetic fields.
Yes, indeed.
Yeah. And on kind of motor topologies, like one of my pet topics, as many people listening will know, and actually the reason how I kind of came across you some time ago was the axial flux motors. So we're kind of seeing some activity now with axial flux machines. My personal feeling is there's a lot of potential there for axial flux in the market, and when people, I do think the lack of axial flux is partially down to the lack of the simulation tools, 3D. Having had to model axial machines myself, or not actually myself, the clever people that worked with me did that, but it was quite difficult because you couldn't do 3D simulation of the electromagnetic fields easily, so you always had to sort of transpose it into a design that you could model and then convert it back, and there was an awful lot of it was difficult and not overly accurate. So designing an axial flux machine has been quite hard to date because it is a 3D magnetic flux in that machine. Do you think that we might see more activity around axial flux? Do you think there's potential there? And by the way, you are allowed to say no, because I'm not. It was a pet topic, but obviously I'm not involved directly in that anymore. So I'm easy either way. That's an honest opinion.
Yeah, I think so. Well, obviously the field is booming right now. We are seeing lots of interest in axial flux machine. I think Mercedes acquired Yasser, which was one of the maybe most known players on that field.
Yeah, someone said to me just yesterday, they were saying Yasser is a technical term, not a brand name. They were sort of a little bit offended by the fact that they've got it. But they've been around for a long time. Yasser with the Taurus style axial flux machines, so sort of dual rotor, single stator, which has some really neat potential in terms of packaging and power density and things like that, but some issues as well, torque ripple and noise being a couple of those. But yeah, it is interesting that Daimler have acquired that business to bring that product in house and really sort of scale up the production. Do you see other kind of activity around axial flux?
Well, activity is there, of course, plenty of players on the field. And well, I do think that the topology itself, it offers some benefits. So it's not all hype there. Like you mentioned, you can get a nice torque density, especially in smaller machines, like the kind you usually have in EVs.
Yeah. Oh, good. So then the nature of your work means that you're seeing what people are thinking about doing a long time in the future. So you're sort of involved in that early stage, helping people create concepts and work out machine designs. If you had some tips or thoughts on future technology trends in machine design and the direction of travel, what would you say they are?
Okay, maybe of the trends, again, if we consider like traction or aviation applications, is that the speeds are going up. And by speeds, I mean the RPMs, the surface speed of the rotor, the electrical frequency. They are all going up a bit at least. You are seeing more and more high-speed applications. And that's precisely because of the fact that it's easier to get a nice power density and a smaller machine when you have a higher speed. Again, of course, you may need a gearbox for that, which is one of the trade-offs that you will have to consider.
Yeah.
But anyways, the trend there is evident.
And this is, so my take on that has typically been that in an electrical machine and the power electronics, the thing that costs you money is current. And by going to higher speed machine, you can have the same sort of torque output through a transmission, etc., but for much less current at the machine or through the electronics. So you can kind of reduce the size of the machine, take copper out, take magnet out, take the active materials out by going higher speed, and actually reduce the size of the electronics as well, potentially by going higher speed, but still achieve the same driveline performance. And the sort of rule of thumb in my head, to a point, because this isn't true when you start to get into bearing problems and things at very, very high speeds, but mechanical torque. So mechanical torque is cheaper than electrical torque. So a transmission,
Yes.
To give you trying to do a low speed, high torque motor is typically a lot more expensive than a higher speed machine coupled to a transmission using some mechanical advantage there to give you the torque output that you want. Do you think is that the key thing that's driving it? And if it is, do you think it's costs? Like people try to take cost out of the system, or do you think it is all about performance? Because the other thing as well is that even with the transmission, typically that system will be significantly lighter because you're getting rid of steel, magnet, copper out of the machine. Is it weight that's driving the high-speed machines, or cost, do you think?
Well, depends again who you ask. In an EV application, I think it might be a combination of cost and efficiency.
Okay.
And efficiency, of course, is determining the battery cost.
Yeah.
Like how many kilometers you get per kilowatt hour determines how many kilowatt hours you need in your battery. And the batteries are still one of the most expensive components in the car. So
Okay. And the efficiency, I hadn't really thought about that actually. So a higher speed machine, do you think is that because you can reduce the ohmic losses in a high speed machine? Because you're going to have the more you push the speed, you're going to have other significant loss mechanisms coming into play. But from an efficiency point of view, what's the key driver there?
yeah, most of the time it's the ohmic losses that get reduced because, well, simply put, you can have a smaller machine, a smaller volume of copper producing losses, so the total losses will be smaller, of course. Of course, when you go to higher speed and higher frequencies, the iron losses mainly, they will grow. Also, if you have any conductive bodies in the motor, the eddy current losses will grow as well, but usually the iron losses are the most significant of those two. Now, regarding the importance or relative importance of copper losses and iron losses, that again depends a lot on the application and the type of the machine, how it's loaded, how it's cooled, what kind of operating point is it's operating on. If you consider the rated point of an EV motor, for instance, usually they are mostly copper losses, and the iron losses are more significant at those low torque, high speed operating points that we also discussed earlier.
Yeah.
If you consider aviation motors, they are usually, at least the kind of prototypes you see in published literature and so on, they are usually much more heavily loaded, and they are almost all copper losses in order to get the kind of power density they want.
Okay. It's interesting. So sort of two different mechanisms, but the answer potentially is similar. in terms of higher speed. And when you say, do you sort of see a point at which the speed stops? Like, is there a practical limit, or could we see a 30,000 RPM traction motor in the future, do you think, or even higher, 40,000 RPM traction machine?
I think that is mostly a question of the transmission, what is practical to build, which is outside my expertise again.
I just heard a few transmission engineers collapse up the street at the prospect of dealing with a 40,000 RPM motor. I think I certainly hear a lot of people, 18, 20,000, there's significant challenges getting the reliability, durability on that sort of transmission system. So it'd be interesting to see how much further it can be pushed, and maintaining reliability and of course efficiency in the transmission. Very good. So I'm just mindful of the time. We've actually run out of time, so apologies for taking you over there. But in a final word, looking forwards, what are you what are you most excited about in the next year?
In the next year, that's a short.
Sorry, years plural. That was me. In the next few years, what are you most excited about?
In the next few years, let's say, well, all kinds of things. Traction, of course, one of my pet topics. Aviation, especially. Let's see what way that is going to go. If the eVTOL bubble is going to burst, like some people predict, or not. If we actually will have flying cars for at least some folks in the future, that's interesting to see. Regional aviation, if we are gonna be seeing electric planes carrying some 2,000 passengers for shorter distances than the planes nowadays are doing. That will be cool to see. So maybe those two things.
Oh, interesting. So, Antti, thank you very much for taking the time. It's always fascinating talking to someone who's so deep in the sort of technology development side of things. I'll put some links in the show notes for people so they can find you and find what you're doing at Smeklab, and hopefully if they want some challenging machine design problems looking at, you might be able to help some people out in the future. So again, thanks for taking the time out to talk to me today.
Thank you.